We'll wait for a few more minutes. Let's wait for a few minutes if there are any other people joining. Okay, so I feel people will join in meantime. So we'll start the class. I mean, it's just for 2 hours. So yeah, so I will greetings of the day to the one who's present and to the people who will watch this on YouTube. I am Swastik Sharma. I welcome you all to this week 3 doubt clearing or problem solving session for the course Smart Grids Basics to Advanced Technologies being taken by Professor NP Padhy and Professor Premlata Jena. I am Swastik. I'm a PMRF scholar at IIT Kanpur and I'm a TA for this course. Let me share the screen. Okay, in the last few classes, we were discussing about smart grids, right? First, we discussed what are smart grids, why are they smart, and then we moved on in the second class. We discussed uh, two main DERs that are present that are shaping the future of electricity generation, at least at the for the to increase the renewable energy generation inside our country and all over the world, right? And the two we studied were solar PVs and the other we studied was wind power generation, right? And the common characteristic with both of them is that they are intermittent in nature and variable. So, right, this intermittency and variability, it affects the system operator because it has to continuously match the load with that of the generation, right? And generally, what happens is these renewable energy generations, these are treated as negative load, and we just they just inject power, whatever they make, they inject power to the system, right? And what really happens is for the solar power, it leads to, because it's only available during the daytime, it causes a phenomena called as, that we discussed yesterday as well, it's called as duck curve. So we'll discuss duck curve today as well. So this duck curve, what it happens is that it affects the system operator who has to manage the loads, and for that he's looking for newer you know devices that can help him in manage these in a better way, right? So the one thing that is commonly being explored across all renewable energy generations are the storage devices. So these energy storage systems, these uh, these help the system operator to form these uh, uh, intermittent renewable energy resources. By firming, I mean because their output is not constant, it varies. Let's say the average is like this, it continuously varies, right? So to form this, to have a controllable or an output that can be used to be able to better sustain the system fluctuations, that is what storage devices can help. Not only that, it's not limited to that. I mean, there are other benefits as well. We'll discuss all of this in a few seconds, right? So first of all, the benefit that they offer is that they have location flexibility, right? We don't have to I mean, we don't have to spare large amount of spaces, at least, like the ones needed for thermal power plants. They can be integrated easily. Let's say you have a solar PV plant on your rooftop, you can connect a battery to it, right? So the location flexibility is very important aspect of the storage devices. They can just be, we'll study in the next few next few minutes about the sizing and siting of this energy storage system. So we can have them configured anywhere in the distribution network where we want them to be placed, so that they can result in optimal generations, right? And they can help form the variable renewable generation. That's what we were discussing. They are very intermittent in nature. So let's say you forecasted that your solar output will perform at its peak, but it didn't, right? And now you have promised some sort of, energy to someone. So you can use the storage to, support that extra amount of power that is needed, just because your solar was not able to provide, because it is intermittent. It can also support in decarbonization. If let's say that it helps you configure how you want to, it helps you in configuring these renewable energy resources in such a way that they can firm their capacity, right? So if this in turn leads to their adoption. So the rate of it leads to the increase in their rate of adoption, and hence, because it's coming from a cleaner fuel, and you don't have these fossil fuel based power plants, so you can have decarbonization of the overall grid, right? So they can help. I mean, it's not like they'll only be responsible for decarbonization, but they are an important instrument. The other thing is power reinjection, right? So whatever they can consume, they can reinject. So you don't you don't have to feel like, okay, so what you can do is you can store at times when the generation is available, solar is available and load is less, and you can just re-inject it when the need is there. So we'll discuss all of this one by one. It's just that I'm just showing what the need is. Next is controllability. You can control their output. That is what is missing with the renewable energy generation, right? You can't control their output. I mean, you can by not operating that at maximum power point, but still, the amount of controllability you have with the energy storage devices is much more than what you have with renewable energy generation, right? So this is the timeline how it all began. So it was first the fuel cell that was discovered. So what is fuel cell, right? So you must have heard about the phenomena of electrolysis, right? So what you do, so basically how this operates is, it's given another name. Let me change the pen. It's called power to gas to power. This phenomena is called power to gas to power. So what do I mean by power to gas to power, right? So for electrolysis, you first need electricity, right? So what you do, you when you have surplus electricity available, you split water to H2 and O2, right? So let me just take a note on the page. Okay, this is black. Let's work on it. So it's visible, right? Hmm. So what you do, your first step is electrolysis. Okay. Yeah, can you mute yourself, whoever joined recently? Um, yeah, can you mute yourself, Sundar Pandyan? Yeah, thank you. So, so what you do when you have surplus electricity available, you split water into hydrogen and oxygen, right? H2 and O2. That's what you get, right? And then you store this hydrogen. You store this hydrogen in gaseous form, right? It in compressed state, liquid state, however you want to do, however it is, uh, I mean, convenient to you, or in solid shape or form. And then what you do, you can use when you have periods of, let's say, high load demand, uh, you can generate electricity from it. So how does that work? So this hydrogen, this H2, when you have this H2, you can feed it to a fuel cell. So this H2 is fed into a fuel cell, and this fuel cell, through a series of electrochemical reactions with oxygen, it can produce electricity and water back, right? So this is a very common phenomena we have all studied in our school. So this is what a fuel cell does, and this was the first form of energy storage that we could have thought of, right? Then there came lead acid battery. So lead acid battery was one of the first ones, yeah, right, where a practical rechargeable kind of a battery was produced. Then someone named John A. Howell for military applications developed a flywheel energy storage. So what is flywheel energy storage? So if you have seen, if you went to a tailor shop, he has this he has the control over his foot, and he stomps on it or taps on it, and what happens, there is this revolving wheel kind of a thing, right? It revolves, and it continues revolving for a certain period of time, even after he removes that tapping or the force that he exerted on it, right? So it continues to roll until the inertia gives away, right, due to friction or anything that is there. I mean, there's no ideal frictionless surface, right? So this flywheel continues to store that energy in form of kinetic energy, right? And what can it be done? It can be then used to transmit this amount of power by using it as a motor or a generator, so that you can use this stored energy in some form, some shape or form, right? Then nickel cadmium batteries were developed. They were then these were advanced version of lead acid battery. We will discuss how they were different. But yeah, then nickel cadmium came. Then you had pumped hydro storage. I specifically remember teaching you about this in first class. So what are pumped hydro energy storage? What you do is similar thing like how hydroelectric power plants work, but it's just that the quantum of power is less, and the you don't need it. You don't need dam as such. So what you can do is, when there is periods of let's say low load and generation is more, you can use that power or energy to have some water, and you can use it to be stored at some overhead tank, right? And what you do is you store this water in some form of a potential energy, which you then use small pistons, or you can use some small cylindrical tubes to inject that water onto a turbine. This turbine rotates and it generates electricity. This is called pumped hydro storage. Then you had superconducting magnetic energy storage. So what is a superconductor? A superconductor is kind of like a resistanceless material, right? It can without any resistance, it can continue the flow of electricity, right? So without any resistance, what happens? You use some form of a DC current to energize it. It stores this energy inside in a magnetic field. And why magnetic field I'm saying? Because the current keeps on rotating inside. It's a resistanceless surface. It keeps on rotating, and when it's needed, you can use that electricity to use that current to in some shape or form. So you have to first convert AC to DC, and then this DC current back to AC. So this was also developed. Then you had compressed energy storage. So air, when it's compressed, the pressure is very high, right? And you can use this pressure to inject it to some sort of a turbine or something where you can use this form of energy. So all in all, what you're doing is you are using the energy and you are converting it to like kinetic energy or potential energy, so that it can be used for different ways in which you can harness this energy, not specifically for electrical purposes, but for any purpose that you want. Then you had supercapacitors. Supercapacitors are these capacitor which has low internal resistance. They have this the- this electric field inside of it. They have this some dielectric medium in which you store charge in form of electric field, right? And what happens is this supercapacitor, these are very high in power density. When I say power density, they can supply power in a in a very quickly. So this power density, so these are high in power density. So power density is nothing but power output per unit volume, right? So it's meter cube and this is watts. So these are very high in power density. They can give a very large amount of power output per unit per metric cube of volume they have. Then the present days lithium ion batteries that you use in your electric vehicles, your phones, anything, laptops, anything of that sort, right? They were released by Sony in 1991. Now there is currently research happening where we are developing paper battery. Why paper battery? These are cellulose based batteries in which you use the dielectric medium of this cellulose to store charge. And these are currently in development. So I recently read an article, I don't know, not recently, it was long back, but it was of some Chinese laboratory where they have developed these thin paper based batteries which can be twisted and turned. So film based batteries. So we have made a lot of progress, right? From where we started fuel cell, and now we have come to this paper based battery. So batteries are evolving. The lithium prices, it continuously is going down, and it makes sense to use them as part of, our renewable energy generation means. So and we've clearly specified their need as well. So these energy storage systems can be classified into thermal energy when you store them in some form of a thermal or characteristic of energy, right? So these include thermochemical energy storage. Then you have mechanical energy where you have pumped hydro and flywheel. There is one more concept gaining right now. It's called gravity energy storage. So we have in our IIT Kanpur one incubated startup. It's called Board Resources. So I recently met his founder. So what they do is, so see, water is not available everywhere, and water, it can leak, it can cause so many things, right? But you have sands or some point of a medium available, right? These small particle sands, like take the example of silt or sand. So you can use these sand at the period of low load. You can use the extra amount of energy or electricity to use the sand and take it to some overhead place. So let's say, so you have sand here. So what you do, you take the sand, keep it in some overhead compartment. This is overhead bin. And this sand can then be used to generate electricity by supplying it in some form of like piston-based materials, piston-based tubes, right? And these are connected to a turbine, let's say. I'm not doing a good job, but just take it for, it's just for representation purpose. Don't, it's not the actual drawing. So it rotates the turbine and we can generate electricity. So you see, we have come a long way. Now we have gravity based energy storage as well. So people are using that too. Then we have chemical energy where we use hydrogen energy storage, just like some form of electrolysis we do. We get hydrogen and then store it so that it can be used later. And we have electrochemical where we have battery or flexible battery. Again, flexible battery is again these newer batteries which are thin film wire based, these batteries which are being developed, right? So these this is just the classification, same classification, chemical, electrochemical, thermal, electrical, and electrochemical based. And we have different pumped hydro, compressed air energy storage. We have flywheel, lead acid batteries. Then we have lithium batteries, flow batteries, sodium batteries, zinc batteries. In thermal, we have sensible. So what we say sensible, um, you have these solar water heaters, right? So what do these solar water heaters do? They at times when solar energy is there, they uh, they uh, they increase the temperature of this. Yeah, you can you can always unmute yourself. You don't have to raise your hands. Yeah, Deva, you raised your hands. Okay, just when you want to unmute yourself, you can unmute. No worries. Right. So, so what you do is, so these are sensible thermal storage, so like modern salt or chilled water. Then you have latent. Mm, what happened? Okay, just a second. Hmm. Audio is working, right? So and we have thermochemical storage as well. In electrical side of it, we have superconducting magnetic storage where we use DC current and store it in some form of a superconducting material so that it can be later used. And then we have supercapacitors as well. And in chemical, electrochemical based, we have power to power or power to gas, just like fuel cells, right? P2G and G2P. It's in short, it's P2P only, right? You are using P2G2P, but I mean, it's power to power. You're using power to get power. So this is what the roadmap is. So India has set ambitious target, but we are very close to reaching it. I mean, last time I checked, we were very far, but now the BESS has strategically been invested by POSOCO, and they are using it right now. So if you see this map, I mean, it's not. I couldn't get a very high definition version, but you can always go to Niti Aayog's website, and you can get this energy storage roadmap. So you see Based on how much solar rooftop power we have at peak, we want to have as much ESS as we can possibly get, right? So this is what we have. So you can see at in Gujarat we have currently 1451 megawatt of ESS energy storage. I'm just talking about ESS, not battery as specific, just ESS, right? So we are far, but we are reaching that target slowly, slowly. Now, I talked a lot about, right, why we require, what we require, but the main thing that comes is that their their use case is evident in system operations, um, on in system operations, and this is why we need ESS from the power system perspective, right? From the power system, there are a lot of things that are happening just because we have renewables in the picture. Everything was fine when we had coal-based power plants. Then we thought, okay, we have solar, so let's get solar power. And from them, from then it started. We started having these difficulties in our system because traditionally we were not ready to handle these uncertainties or intermittencies or vulnerabilities in the system, right? But now we need to have some sort of a, because we have commitments, right? We have made commitments of climate change, so we want to have renewable energy generation. We have a lot of commitments to fulfill, and for our coming generation as well, we want to give them the environment as we got them, right? So we need to increase the deployment or of renewable energy generation in our system, right? And this is how BSS helps from a system operation perspective, right? You see, you have issues like, because there is a lot of intermittencies, so we can have issues like frequent. Just a second. Yeah, there is. I thought I didn't have. So I'll just keep it here. I want to discuss dark curve next, so that's why. Yeah. So from the system operation perspective, there is this intermittency, right? It can generate at any given point of time. It can increase and decrease at any given point of time, right? So it becomes hard for us to regulate frequency, because to have frequency regulation, we need to match generation with load or demand, right? It keeps frequency neutral. As P load becomes greater than P gen, frequency starts dipping, or P load becomes less than P gen, frequency starts increasing. So frequency criterion, and it to be within that 49.9 to 50.05 band, we need to ensure that we can get as much frequency regulation as possible, right? And how can we get frequency regulation? It's through power only. So active power has a direct correlation with frequency, and that is where best comes in place. It can supply, it can give a response in like milliseconds. So when I say millisecond, why I say millisecond? Let's say, this template is very bad. Just let me change it. uh, oh, sorry, it should be white, right? Okay. So when I talk about this is what happens. Oh, sorry, why do I even need that? See, what I mean by frequency regulation, it's like this. This is P. Let's say this is time. So when we draw load curve, we draw it like this, right? It's like smooth curve, but it's not smooth in general. If you check website Posoko's documents, and they have these review reports, if you see them, you'll see that these are actually very, very intermittent. It's like this, right? So how can you match this when you have a lot of intermittent, I shouldn't say intermittency, variable, you know you have this varying curve. So how can you match it? So for that, we want frequency regulation, and because best can provide it in a very quick time, we can use them. Next, let's say we have load this duck curve happening, right? What is duck curve? At periods of when we have this solar when we have sunlight, when there is period where we have daylight or sunlight, the load is less. So we at typical residential load, it follows these two peaks. One an early morning peak, and the other, sorry, this is very bad. One is an early morning peak, and then the other is a late evening peak, right? So when you have daylight or sunlight available, you are just your load is less, right? And because sunlight, solar power is treated as negative load, it's just fattening the belly of this curve, this duck, right? It's fattening it, and by fattening I mean the point from this to this is increasing, right? Let's say that this was 1400 or 1500 for representation purposes only, and this is 500. So now in a matter of, let's say, uh 3 hours, you need to turn down 1000 megawatt of power. So you want to remove 1000 megawatt of generation from the system in 3 hours, and that is not achievable with coal-based power plants. So coal-based power plants are divided into subcritical, supercritical, and ultra supercritical, right? So all of them have different ramp rates. So this is what ramp rate is. Ramp rate is how much you can shed, or how much you can generate or remove per unit time. So it's delta P by delta T. This is what ramp rate is. I should write it like this. Now, so the exact, so one clarification I would give, I'm not good with numbers, but you must check this at your own, but I feel this is pretty. So 1 to 3% for subcritical, 3% to 6%, and then 6% to 8%. This is what their ramp rate is. So when I say percent, what I mean is, let's say that your maximum capacity is 1000 megawatt, and if you have 5% of ramp rate, that means you can 5% per minute. So when I say percent, it's per minute, right? It's 50 megawatts per minute, right? So this is what the ramp rate we have for supercritical, subcritical, supercritical, and ultra supercritical coal-based power plants, right? And and they have one more effect. It's that if you turn them off, if they are not committed, they require a certain amount of period before they can start. It's called cold start time, right? And this varies from all of these. So it's like 6 to 10 hours for this. Uh, Again, I'm not good with numbers, so you should check 5 to 8, I guess, for this, and then we have 3 to 5, 3 to 6 for this. So you see, you require a certain amount of time before, if they are switched off, you need to turn them back on. So this is going to be, so it is a challenge for system operators worldwide. So this particular curve, it's not for our system. We don't I don't have a duck curve for our system yet, but this is for New England ISO, and this is what they have been explaining, right? And they what they say is that below this dotted line there is a potential for grid instability, and this solar curve, excess solar PV generation and injection into the system is causing this. It's fattening this curve, right? And then there is this extreme jump again. It's from 500 to, let's say, 2500. So it's 2000 megawatt in like 6 hours. So you see, you have so much, you have such things happening in the system, and the system operator has to be responsible for this. And that's where this comes, best comes, because they don't require any startup time, they don't require any, they don't have a ramp rate, they can provide response in a few milliseconds, right? So that is where their frequency regulation comes, right? And then they have flexible ramping. They can flatten the load duct by curve by suitable ramp, so they can ramp easily, and they can flatten the curve. So when I say flatten, what they can do is, at periods when you have high solar energy, you don't inject that into the grid. Use it to charge your energy storage systems, and then discharge them when you have peaks available, right? And this is also called peak shaving or energy shifting. And these can also be used for black start services. So when blackouts happen, the electricity is totally removed from the system, right? And these coal-based power plants or any of these uh, uh, any of these power plants, they require certain amount of electricity before they can come back into operation, right? There are auxiliary power units and certain stuff. So you need some sort of a, some sort of a backup to provide this. If there is no electricity into the system, how will you ensure that, the system emerges from this blackout? That's where ESS comes and plays a big role. Then we know that, right? This is what, from a system operation perspective, they can do. Then we can use them for investment deferral. So a transmission system is very costly. So when I say costly, transmission systems are there from a very long time. When you can't, in 5 years or 10 years, keep on upgrading them, because a lot of challenges are faced. You need to get transformers, you need to have certain suitable substations and stuff like that. So for, let's say, a developed city, and now the load has started to increase, so you just can't keep on investing every 10 years. So you can defer that investment. When I say deferral, you have to have that investment made in future, but you can defer it for time being by using BESS. How? I'll just say, let's say I have a two bus system, right? A very very basic example I want to give. And you have 50 megawatts, right? And this tie line, it supports only 25 megawatt. It's a two bus system, and this transmission line supports only 25 megawatt, right? This generator A and generator B both have a maximum capacity of 25 megawatts, and both of them supply 25 megawatt, right? Now let's say, okay, I shouldn't say 25, I should say 30. Let's say the maximum capacity of this is 30, right? But let's say both of them supply equal 25 megawatt to supply this 50 megawatt load, right? But now this tie line or transmission line has only 25 megawatt of capacity, right? And let's say the load increased to 60 megawatt. Now, I shouldn't say 60, 55 megawatt. Now, this extra 5 megawatt, if the transmission line could have supported, could have come from this generator A, but it cannot, right? So, what can you do? You have to replace this transmission line, right? But that's not the only thing you can do. What you can do is you can defer that investment. You can defer that investment by having an ESS or an energy storage system connected to this, right? This energy, I'm not saying only energy storage systems can support investment deferral. Any DER can support it, but mm, because we are talking about the ESS, I'm just talking about the benefit right now. So ESS can supply this extra 5 megawatt for the time being, right? So this is what I mean. So what you can do is this supports transmission and distribution congestion relief. This is what we talk about congestion, when the transmission line cannot support or accommodate any extra power, right? Then we say that it has the transmission line has congested. Also, we can do energy shifting. What do we mean by energy shifting? So whenever you feel any doubt, just unmute yourself. I'll be happy to answer. So what I mean by energy shifting, again, for a residential load, eh, right? This is how we say. I mean, don't, it's not the exact replica, but just, right? So, what I mean by energy shifting, it's like, let's say that, your ESS, you want to charge here. Don't charge here. You can charge it when the loads are less, right? This load is less, so you can charge it here. So, what happens? The energy that you were going to consume here, I shouldn't say like this, right? When you were going to consume here, you will consume here, right? So, now the curve becomes something like this, and this softens a bit, right? This peak is a bit softened. So this energy shifting results in peak shaving, which then can be used to supply this load. And when this load is supplied, you require less amount of energy from the grid. So you see, you can shave the peak by using energy shifting and energy storage systems together, and you can use them to supply when the period of when the peak is happening or occurring, right? Or as you all know, when there is peak inside in the system, the prices are more. So whenever I say peak, it means that the prices are high, because low, when it's the same, it's demand and supply game, right? Demand is more, supply will be more, and supply will be from the expensive resources too. So by acting as some sort of, some sort of an energy shifting tool, you can use them, and you can defer the investment in sort of like paying for this extra price that you had to do for the peak, to manage the peak. Then you have PV and wind generators, right? You can use them alongside your PV and wind generator to form to form their capacity. When I say form their capacity, they are intermittent. They vary very much, right? But by using ESS and control algorithms, suitable control algorithms, you can use them to discharge and charge in certain amount of way that you can get average, or continuous output from the system, not varying as such we are getting, right? So that is how, when I say firming, it's like when you forecasted more but you are producing less, you can use the stored energy in the storage system to supply this extra energy. And you can use them in mini grids or micro grids as part of, so mini grids and even micro grids, they have diesel generators. So when they want to act as islanded grids, and to supply that, when they have to come to terms with the when they have to connect again with the grid, they have to be synchronized, right? So diesel generators act as some sort of a frequency regulation tools at when they are islanding, and you can use batteries. We'll discuss in week 6 or week 7 how batteries act like this, but right now, just take it from me that they reduce the reliance on diesel generators for the same purpose for which the ESS can be used, right? So you see, we have such things happening, and the system operator is continuously facing a lot of, um what you say, a lot of difficulties in managing this load, demand and supply. And that's where batteries could, energy storage systems could come, right? We discussed all of this: frequency regulation, how capacity, investment deferral, then reduce reliance on frequency regulation. It's the same thing, right? And coming to the India's battery energy scenario, so as of last I checked, we have 219.1 megawatt hour of battery storage capacity currently, and we planned for 236 gigawatt hours, right? So we are far, 2031 to 2032, but let's say how much of it can be developed by that time. So you see, even now, POSOCO or Grid India, I shouldn't say POSOCO, Grid India, they have they each year they release some sort of, research projects for Indian institutions. And this time the central theme is battery energy storage systems, how they can be used, how can be, even I remember we once went to Grid India's office to, demonstrate something. So I work on power market, so we were developing something, and we just went and met them, and they were more interested in how we were using BESS, right, in our wholesale power market thing that we were doing. So their interest lies in this BESS, because that is the need of the hour. With the increase in renewable energy generation, that is where they are coming into picture. Right, we discussed all of this type of ESS in the previous slides. Now, the basic things in which they do develop is the high energy density. So, lithium-ion batteries have a very high energy density. When I say energy density, it's energy stored per unit volume, right? So we have lithium-ion, which have high energy densities. Then we have power density, which are supercapacitors have very high power densities. So, there can be some transient peaks, microsecond or some peaks. Batteries alone cannot support them because they don't have high power density. So for that purpose, supercapacitor is used to supply that transient peaks, And this power density is nothing but power output per unit volume. So their response time is very less. We just discussed that they can just quickly provide energy as soon as they are connected, as soon as we want them to do. So their response time is more, but they have certain cycle life, so they can only hold on to some cycle life that they have. So currently it's poised for 2000 to 3000 cycle life for lithium ion batteries. So when I say cycle life, it's this one cycle is from 0% to 100% to back to zero, right? That is considered as one cycle. So from 0 to 100 and back to zero is considered as one cycle. Or you can say charging and then discharging to the and then charging again back to the maximum amount of energy that it can store. But one thing is for sure, they have high efficiency. The losses are very less in these batteries, right? And they can be used to defer the upgrades, regulate. So frequency control we can do. We can also have voltage regulation. But you'll say, okay, it's the voltage regulation comes from active power, right? Active power controls voltage, so they can also do. So BESS supply DC, they are converted into AC by using inverters, and by changing the firing angles of these inverters, we can modulate reactive power, and we can also have some volt var control where we use some capacitors in conjunction with it. So we can have voltage regulation only, but at certain nodes only to which it is connected. And the ramp rate is very high, just what we discussed, right? So a typical you know, how does a battery energy storage system look? It looks something like this. So before connecting to a grid, I just told, right, it is connected to an inverter which converts the DC to AC. And this inverter has inherent losses. So the first pair of losses before we get the same amount of power that we want from it, it's the losses that come from the inverter, right? Inverter losses. And then we have some idling loss. Sorry, sorry. My bad. Yeah. Where was I? Yeah. So inverter. So the use of inverter is just to convert that DC to back to AC because we want to use the AC power, right? And and we can also modulate the control over the reactive power as well from this inverter, and that's where inverter also has, you know, every component is not purely idle in system, right? So they have losses, and that is where it contributes. Then we have idling losses as well. It's not like if it's just there and it does not have any kind of, you know, let's say your phone, if you don't use it, don't you observe that that 100% has went to 90% if you don't use it for a day? Why does that happen? Because there are internal applications without even you using it for your own purposes. It has internal system going on which requires power. So let's say thermal control, thermal energy control, right? So the battery needs this thermal control where you want to control the temperature, right? So in that, in itself, that causes these losses. So that is modeled using idling losses in kilowatts. This state charging discharging is modeled as a switch. This is a switch. This is just a flow diagram of how the stored energy is converted back to the energy that we use. And then you have charging or discharging losses, right? So you can't, you don't have, you have some efficiency, right? You can't have perfect charging. Not 100% of power you withdraw from the grid to charge your battery will be used. Some will be lost in, let's say, the metal contacts that are there, or internally anything is happening. So there are losses. So there are two efficiency to model it. It's called these two, if these two are what do you say, the component that are used to model these losses, and this is how your stored energy look like. It's is using companion mode. I don't know what that is, but if I'm visible and I'm audible, it should be fine. So the stored energy, yeah, that is what the stored energy, right? If you have the stored energy, this is the ideal storage. If you can get all of the stored energy into for whatever purposes you require, but that's not what happens. Some of it is lost in discharging or discharging losses, some in idling losses, and some in your inverter, right? So what you get is some after removing the losses is what you get, the what you have on the system, right? So just a simple clarification, some people don't know what depth of discharge is. So SOC tells you, so SOC is nothing but amount of energy that is there at present in the battery and the total energy that it can support. Total, E total I'll write, or E rated is best, right? The rated energy that it can store, this is the SOC. SOC is generally measured in percentages, where it's just the energy stored divided by the total rated energy, right? So DOD is nothing but 1 minus SOC. It's called depth of discharge. how much SOC you use from the maximum amount of SOC that is there. So maximum is 1, and depth of discharge is this. So I'll just leave this statement with you. Let's make this class a bit more interesting. So let me ask from you, right? I'll just have the system. You just tell me whether it's true or not, right? Low DOD and high DOD causes damage to the battery. Have you ever heard of the statement? Anyone who knows why low DOD or why high DOD is damaging or detrimental to battery? You consume less or you consume more. If you do or you consume very high, whatever you do, you are causing damage to the battery. So this is a statement. This is true, but why is it true? Can anyone tell me? Okay. So what I'll do is I'll leave this statement, and let's discuss in next class. And I'll remember to discuss. And this is just what I'll write it over here. I'll share it with you. So it's why low DOD or high DOD is detrimental to a battery, right? And don't use ChatGPT, Google. Think, just think. I mean, it's very easy to gauge why would it be so, right? So this is what the SOC versus DOD is. DOD is nothing but 1 minus SOC, where SOC is just the amount of energy stored at a given time, and the total rated power, right? To mathematically analyze your battery, there are several types of modeling that you can do. You can do electrochemical modeling. You can use a data driven or an empirical model, which is called a statistical model as well, where you use data to model how your battery would behave. And one more way you can model it is using an equivalent circuit model. An equivalent circuit model where you connect RC circuits to model how your battery will behave. Now, why RC? Why not RL? Can anyone tell me why RC? Why not RL? So, you know, why RC? I mean, first of all, why RC? Why do you think RC is the best way to model it as an equivalent circuit model? This all has been, one thing I would like to tell you. I mean, I think I've told in the previous section as well. This doubt clearing or problem solving session is not a substitute for your regular course. You have to go through them because they cover 5 or 6 hours of material over there, and I just have 1 hour to summarize everything, right? So it's not possible for me to cover everything or touch everything. But yeah, and Mayur, I remember you, right, from the first class. I will discuss about that as well. So stick around. So why RC? Can anyone tell me? So so uh, RC circuits store electrical energy in form of electric field, right? But RL stores it in form of magnetic energy, right? And we know from our from our analysis that there is this is called an electrochemical energy storage device. The battery is electrochemical. It has chemical based substances in it, right? Like lithium ions and stuff, right? These are dielectric in nature, so they can store some form of electric field. They have cathode, anode, and what happens is the lithium ion is pushed from cathode to anode, and from that you have a constant VOC. So I won't go into detail about how it works, but that is just the crux of it, right? So there is this electric field that develops, and that is why capacitor is used to model it. Another thing, we don't have windings in between, right? And we don't have windings, we don't have magnetic field inside of it. So it's just pure electric field pure electric field that is causing all of this, right? So that is why it's best to model it as RC, right? So what we have right now is this R naught, this first resistor R naught is used to model the inherent losses that are there in the system, right? A system can have losses, right? That's what we were discussing. So this is just the inherent losses. The RC model, what it does is it is used to depict the conditions. It is used to mimic the conditions of how the electrical energy is stored and fit back into the system, right? And since a pure is not there, there is always some internal resistance. That is why we model it as RC. And this is a 2 RC model, even though I have N here, but it is a 2 RC model. We have only 2 RC combinations. And as the number of RCs increase, if you increase number of RC circuits, you can achieve near to ideal modeling. It can never be purely ideal because there are a lot of assumptions that go into making this equivalent circuit model. But as you increase the number of RC, you can have pure 2, you know. And the self discharge is there. Let's say when what happens is there is inherent calendar aging, right? If you keep the battery as idle, it will discharge, and this R self discharge is used to model that. And this open circuit voltage, which is voltage dependent, it's dependent on VOC, is dependent on the function of SOC, which is here, right? And this function of SOC is what VOC is. So if you see, VOC can be drawn like this. I mean, it's empirical, right? I have not seen this. I have not done an experiment to develop this. It's just that it can be developed like this, right? It's like this. This is 1, this is 0, and this is open circuit voltage. So with varying of open circuit voltage, your SOC uh, increases. Okay. So yeah, that is how you model. So I'm sorry if you are hearing any noises. I mean, I'm in lab. I don't know where people are. Okay, so this is how you model this equivalent circuit, right? So this is where was I? I was talking about, yeah. So VOC, we model it as a voltage dependent node. It's because this is a voltage dependent circuit, right? Because it's a function of SOC, right? It's not ideal source. So a battery in itself has a lot of degradation. So a battery goes through degradation. So there is the battery cannot, 10 years from now, if you have, let's say, your phone, you know uh, when you have it, even my AirPods right now, I have them for like 4 years. So last year when I used to take this class, they used to last for the whole 2 hours, but now in between 1 hour 45 minutes, they just go, they stop working. So what has happened? The battery has degraded. The amount of energy it used to store when it was fresh out of the box, it's not doing so after 4 or 5 years. So these can be modeled into two ways. One is calendar aging and the other is cycle aging. Okay. Right. So what is calendar aging? So a calendar aging is the inherent loss of an inherent loss of storing this energy into the battery. So it's the inherent degradation that happens over the life period, over lifetime of battery. And what is cyclic aging? So cycle aging is nothing but how you charge or discharge your phones or batteries. They somehow they also have aging in between them. What really happens inside the battery is that they start forming these cracks. So what happens with these cracks is they the amount of energy that they earlier used to store, and there are other reasons as well. There is lithium plating and everything. We'll touch on that in just a minute. But yeah, there are a lot of things happening inside a battery when you charge it and discharge it, when again charge it. So this repeated cycles, what happens is it degrades the performance over time. So that is what is happening, this cyclic aging. It's the loss of, or I should say degradation associated with repeated charge or discharge cycles. And this is one way in which you can estimate the health of your battery as well. So you see, iPhones recently have this feature, battery health, where you can track how much of energy they can store compared to what they were able to when they were fresh out of the box. And how did they do it? They do it by tracking the number of cycle it has been through, right? So these are the two kinds of so there are a lot of because of the cyclic, there is thermal, it's there is temperature. Due to temperature also, when you charge it at high temperatures, you'll see when your phone is very hot, right, it stops charging. It shows charging will resume once it's when the temperature is back at normal. Why? Because at high temperatures charging it could result in further loss of the battery, right? And that is all covered in cycle aging. So this is what happens with your battery. Two kinds of degradation, cyclic aging and calendar aging, right? And over a lifetime, the ESS or BESS is supposed to go through it. You see, these Tesla cars right now, lithium ions have, the price has started to go down. But when they were first in production, the batteries were almost equivalent to the cost of the car if you went in to replace them. Why is that? Because it's not just the battery it's not just the car, because the car is running on battery, right? So if you're going to replace that battery, you have to pay the same amount of price. That's what they said. So it's very difficult to say that they have now gone mainstream, but yeah, it will take a lot of time before everything is mainstream, at least in India, as far as we know, right? So this is what battery degradation is. So what was the other thing I want to discuss? Cycle and aging, cycle aging. Mm, okay. So degradation happens, yeah. So the degradation is normal and it will happen over the period of lifetime, right? And but now models are being developed, and models are being developed to predict the state of health, or the degradation of your battery, how much it has degraded and why it has degraded. And they can also be categorized into empirical, data driven, or yeah, data driven. No, I should say artificial intelligence based, AI based. And then you have physics based. Okay, yeah. So there are three kinds of models which people have developed to get a sense of what how the battery has degraded, what is the state of health right now. In empirical, what you do is based on the statistics. You have data, right? You can just use that data to create some form of numerical mathematical relation between SOC, DOD, and your energy stored using the thermal temperature. There are a lot of papers online. If you want, I can add them over here. I don't remember the exact the relation, but there are many relations that are there in literature. And what you do is you use them to model it as such. So that is how you can do. Other is AI based. You can train a neural network, deep learning or neural network based things to develop some form of uh, what does neural network do? Creates if the function is nonlinear, it creates some sort of a nonlinear function inside itself which you don't know, by just training and testing on the known data that you can supply. And the other is physics based. You can use the inherent electrochemical reactions that are happening. The Arrhenius equation is one such. I don't remember the exact equation. I was reading the research paper a couple of months back. There is Arrhenius relation which is used to model this as physics. So these are being tested, and one thing that that at least I have developed is an AI based method, because it's a non-linear relation, right? You have a non-linear relation between DOD, SOC, temperature. So we got some data from NASA and we use that to calculate the degradation by training our neural network, and we were able to achieve a very good accuracy. I mean, not very good, but it was good enough, like 90%. So that is what you can do. So AI is powerful over there. Right. So this is all that was for battery degradation. Next, the instructor went on to, so you have battery, you know what the battery does. Now you want to properly size. How much size will you require for your particular distribution system, and what is the site at which you want it to be placed, right? For that, what what you can do is you can have some sort of a optimization framework developed. So what is optimization framework? So you minimize or maximize some function with respect to constraints, which can include uh, an equality constraint or uh, mm, your I should say less than or equal to, right? No, minimum, right? So greater, or you can have inequality constraints, right? So this is an optimization framework. Let me touch up a brief on this. So the one use case where they are used extensively is your unit commitment problem or economic load dispatch problem, right? So let's say you have generators which are a subset of generator 1 to some generator n, right? And you know the cost function of each of these, some ax plus b a. So what I'll do is ai x plus bi, right? You know for each of them their cost functions, right? Now what you want to do is you want to strategically choose those generators which can have minimum, which can result in minimum cost. So what you do is you solve an optimization problem. So you write minimum of the cost is given by sum your generators where and their AIs and the amount of units they'll produce, and this is called an objective function. This thing is called an objective function, and you place in some constraints like constraints subject to your power balance constraints. Xi should be equal to d summation of I to n. This is just one simple example that I've written, right? There are a lot of constraints. There are ramping constraints. Then there are, uh, you know, uh, there are ramping constraints. What are there? Forgot. Yeah, there are transmission line constraints, power balance equations, and stuff like that. So there are a lot of power flow equations and other stuff. So a lot of constraints. I'm just not taking everything into account right now. And there is one more constraint, which is a unit commitment variable. This UI is a binary variable which tells you 0, the generator will not be used. 1, the generator will be used. Right. So this optimization framework is called as integer linear programming. It's called integer linear programming. So there are two kinds of programming frameworks for us. There is linear programming and non-linear programming. So what I'll just do, I'll just write linear programming. So this is a linear programming problem, and there is a non-linear programming problem as well. So why is this a linear programming problem? It's because the objective function is linear, and the objective function is linear, and you have uh, your linear power balance constraint, which is the summation of all xi's should be equal to the demand, and then you have a unit commitment variable too. We'll touch upon that. So, right. So this is linear function. So I should say affine functions. Linear functions are, this is not a linear function as such because there is a constant term b, but affine functions. I hope you all know what are affine functions and linear functions. Can anyone quickly raise their hands if they don't know what are affine functions or linear functions? Yeah, you can go ahead. Oh, you don't know. Okay. So, okay. So in basic algebra, right, when we learn about things, we take it for granted, right? When we studied, we said linear functions are those functions which can be drawn with the straight line. Perfect. Linear functions can be drawn with the straight line, right? But in true mathematical sense, linear functions don't include, they are they are just with their polynomial order is 1 and they don't include a constant term. So f of x equals to ax is a linear function. It can be drawn with a straight line. There is another set of there is another set of function which can be drawn with a straight line. It's ax plus b, right? It's also a straight line where it's the y-intercept is b, right? But this is not linear because they don't follow the property of homogeneity or additivity, right? So we call them affine functions. And non-linear functions are those functions which are of order greater than 1 and can't be drawn with a straight line, right? So, so we have another category. So we use the term linear very loosely, but in true sense, linear functions are only without a constant term because they follow the principle of superposition or homogeneity or additivity, right? You know what is homogeneity and additivity? So, okay, I'll just write. Homogeneity means if I give a constant term multiplied with the variable, my function is like this. If it follows, it is homogeneous. Additivity is if I add one more input, f of x1 plus x2, it can be decomposed into f of x1 plus f of x2. And you'll see that the affine function with a constant term does not follow both of them, right? So these are affine functions. So linear programming, they can include both affine or linear functions, and they are called linear programming problems, and non-linear programming problems which don't have linear functions, right? And in this particular case, which sir has touched upon in his slides, I mean, in his lecture, they have this problem in which they want to find the size and the site of the placing the battery energy storage system. I'm running a bit late, but I will try to increase my pace, right? So what do you need? You need network information, you need the cost parameters, and what you want is you want to choose the optimal operation for which you want to achieve, right? So the optimal operation is by determining the size and location of ESS, satisfying the technical and economic conditions or constraints, right? So what is your objective function in which the sir has touched upon? It's the minimization of investment on operation cost, power loss or voltage deviation. Any of these could be your objective function. If you're coming from an economic point of view, you will always minimize your cost. If you're coming from a system operations point of view, you will minimize specifically for distribution side the voltage deviations or the power losses. And the constraints will be your power flow constraints, your ESS operation, upper bound and lower bound on the distribution decision variables, right? Now, one thing I forgot telling you is because this UI, it's a binary variable, right? It's an integer variable. There is a subcategory inside of linear programming problem. It's called integer linear programming, right? So in a sense, the programming problem that I just developed, it's an integer linear programming problem. But let's say in a different, some different problem where this UI is continuous. When I say continuous, it's an element of 0 and 1 where it can vary between 0 and 1. It doesn't happen, the unit commitment is not between 0 and 1, but just let's say it is a decision. Then it becomes continuous. It's called a linear programming problem only. But if you have both, you have your integer variables and your continuous variables, it's called mixed integer linear programming problem, right? And the same goes with this as well. There is mixed integer nonlinear programming problem or integer nonlinear programming problem. And you know, linear programming problems are easier to solve. There are readily available solvers, Cplex, Gurobi, you can access if you have academic a license. And there are nonlinear programming solvers as well. GAMS has one, it's called IPOPT, and you can use them to solve, interior point something. So you can use them to solve nonlinear programming problem. It's just that they take a lot of time. And what you do generally is you linearize your constraint, and that is what sir has also done. Power flow constraints are non-linear in nature. So um, I mean, they are not linear. I mean, if you have seen power flow constraints, I don't know if all of you know, but in distribution side, power flow constraints can be written like this. Uh, then you have, I guess, plus, no, minus Vij Gij cos theta ij plus Vij Bij sin theta ij, right? So this is a transient, oh sorry, this is V and you will have Vij here as well, right? So this is a transcendental incidental oh, shit, just a second, it's not like this, it's Vi Vj So it's a transcendental equation, right? So you have cos terms, you have sine terms, and you have square terms as well. Of you have products as well, vi square, right? So you have multiple different terms coming in between, right? So this is a non-linear function. The power flow is inherently non-linear. What to do is you linearize it. So a distribution level problem, anything you solve at the distribution level, it is a mixed integer non-linear programming problem. Mixed integer because you would want to, some sort of decisions related to turning on or off a tie line or something like that, feeder or substation capacitors. You have 0 1 constraints over there, and let's say the amount of power you want from ESS, it's a continuous variable, so it's a mixed integer non-linear programming problem, and these are very hard to solve. And one more thing, this equation is also non-convex in nature. So I'm telling you a lot of different things, but they need to be told because they are in your assignments too. So so there are two more functions. These are convex functions and concave functions. I won't go into the math side of it, it's very extensive, but yeah, if someone wants me to go, we'll go some other time. So what is a convex function? Let's say you have a circle, okay? If in a plane of your function, this is a function, if in the plane of your function you can have 2 points and then you can connect it with without even intersecting the plane of your function, right? Let's say this point and this point, and if I can draw a straight line without even intersecting, it's called a convex function. But at the same time, if you have, let's say, a function like this, I have 2 points in which it has to cut the plane, then it is a concave function. And concave functions are they can't be solved with your by these programming problems. What you have to do is you have to convexify them. By convexify, you connect these two things so that this plane is also included, and once this plane is included, you can use them as a you know you can use them to solve the problem. So concave functions have to be convexified. And one more thing, if you can see, this is this function is a circle equation, right? Equation of a circle, and the equation of a circle is non-linear. It's xi square x square plus y square, right? Fx is x square plus y square, right? I'll write fxy. So you see, this function is non-linear in itself, right? But it is a convex function because you can have 2 points in which it won't intersect the plane. So this is what, and the any objective, any optimization problem, it has to be convex function before it can be solved. So non-linear or not, linear or not, it needs to be convex first. Then only you need to dissociate if they want to be linearized or non-linearized, right? So this is what they did in their paper. You can feel free to go ahead. We'll discuss this paper once more in the microgrid section where we'll discuss what really happened in this paper. That is why I'm not going to delve on it right now. So you see, now you know all about battery chemistries. Now, how do you pick the battery? You can have multiple of, lithium ion is expensive. You have lead acid as well. It's easier to get as well. So how do you pick that? How do you pick that perfect example? So car batteries, these are not lithium ion batteries. They are lead acid batteries. Why? Because there is a reason. There is a reason. They're cheap, and they're smaller in size. They're lightweight. That is why you have to pick the use of the battery, right? So you see, lithium ion, it has high volumetric energy density and specific energy density, right? So per unit kg and per meter cube of volume, they have very high energy density. While for lead acid, the energy density is very less. And nickel, cadmium, and nickel metal hydride come in between. And the weight is also there. If the energy density is less, the weight is less, but if energy density is more, weight will be more, right? And this lithium ion is currently being used in very in advanced things, EVs, you have e-bikes, even in telecommunication, PV generation, your tools that you use, wind generation, your UPS and backup system, everything comes with a lithium ion battery because it has a high energy density. It can store more energy per meter cube of volume. So these are the advantages and disadvantages we have all covered, and this is just summarized here. You can just go through it once. Now, you see, everything, about the battery energy storage system. They go through a degradation, they need thermal management, You see, in India specifically, the Ola, these e-bikes, they caught a lot of fire in the southern region. Why? Because of the fact that they are not made to support the kind of like the condition, the humid conditions that the Indian environment has, right? So BMS is the one that is the culprit of them catching fire, because it is not able to maintain the cooling or the thermal, thermal management. It is responsible for managing its thermals, right? And it is not able to do it. So this is what a BMS does. What it does is it takes the voltage, the current, and the temperature of the battery. It processes it. It has some sort of, some sort of black box. Consider it as black box. We'll discuss about it later. And what it does is it is used to produce an output like SOC, the state of health, or the fault, if any has occurred, or the status of the battery. You see, there are other many ways in which these are you can estimate the SOC of your system. The BMS is uses some of these components to estimate the SOC, and one is the conventional way. One way in which you can measure the estimate the battery SOC is by measuring the specific gravity of the electrolyte it has, right? The specific gravity of the electrolyte. Um, Let me explain it. How let's say for a lead acid battery, right? When it stores energy, it produces acid inside of it. It's called sulfuric acid, right? When it is at 100%, the concentration of sulfuric acid is very high. When the energy starts dropping, the concentration of sulfuric acid inside the liquid becomes less. And that can be used by measuring the specific gravity. When I say specific gravity, it's the volume of the density of the liquid compared to the density of the water, right? So measuring the specific gravity, we can measure the SOC of a battery as well. So these are conventional ways in which we can do. So kind of like, so if I can give you an example, uh, let's say you had a Coca-Cola bottle, right? So you poured the whole concentration, 100% concentration for yourself, but then there was some left. You poured it and then you added water to it. When you drank the first glass, you experienced, the taste of it and everything. But then the next glass, which had some quantity of water, you were not able to appreciate the same taste. Why is that? Because it was diluted. So by measuring this dilution, we can estimate the SOC. So that is what I say by measuring the specific gravity. Then we have adapted Kalman filtering. So what is a Kalman filter? What it does is it estimates the state of a linear system. It is a linear system. It estimates it by taking in the measurements of the voltage, temperature, and current, and it recursively iterates, continuously updates its beliefs, and produces a state estimation of the battery. You can also use machine learning, your support vector machines, anything which you have, and you can use neural networks, the deep learning things, LSTM, CRUs, or anything to estimate the SOC, right? So these are some way in which you can do. Last item on the agenda was cell balancing. So you see, nothing is ideal. So your batteries could have cells which are weaker, which get weaker much quicker over the time. Why is that? It can be because of manufacturing defects. you know some defect creeped in, you don't know what happened, but now you have one weaker cell compared to other. I'll talk about how this comes. So let's say that you had this. I'll just use a pointer to explain. Okay, so this is how your battery used to look like. When you charged it, you see that there is imbalancing. Some are the concentration of the charge in the batteries is not same, or the cell is not same. But when you charge it, one gets charged very quickly. When one gets charged, now it becomes open circuit, so other won't get charged as well. So when it happens, the others are left with uncharged capacity. And when you discharge them, what happens is the one that had very less charge, which was the weaker one, gets depleted very quickly. It becomes open circuit. It cannot supply power again. So you see, having weaker cells is also a problem. You need to have a cell balancing so that every cell can have same amount of energy, so that it can charge and discharge for the same equivalent amount of energy it has stored, right? And how does that usually happen? It happens due to manufacturing defects. It can happen due to heat dissipation, right? If let's say one has more heat dissipation than the other, it will discharge faster, right? Some can have difference in charge discharge rate. So one cell can have greater charge rate, the other can have lesser discharge rate, and there are other things possible as well, right? And to control this, what we have is two things we use. We use active balancing or passive balancing. In passive balancing, what we have is we use resistors to dissipate the extra energy that the stronger cell has. Let's say there is a cell which has extra energy. I can dissipate that extra energy so that every cell in all of the circuit has same, by connecting this by with a resistor similarly like this. I can dissipate the extra energy so that everyone can have same VOC. When everyone has same potential at the nodes, there won't be any current flowing to the resistor, right? Because all of them are this at the same potential. So this is what you can do, but it is lossy in nature, right? You're using resistor to dissipate that energy in some form of heat or as such. So this is it causes heat dissipation and it is lossy in nature, right? The other thing you can do is you can use switches. So you can use switches to charge the weaker cell from the stronger cell. Use the stronger cell, charge it, charge the weaker cell. That is what you can use by using some control algorithm configured with your switches. So PE based switches or switch, I'll write switches. Right. In the lecture, you must have seen Sir has talked about the mm, transformer based, resonance based, circuitry where you can use it, capacitor based as well, inductor based as well, where you can use them to store energy and then charge the other battery, right? So this is what cell balancing is done. So you just there are two kinds of ways, active and passive, in which you want to balance the amount of energy every cell has. So this is this is all I feel there was to discuss in this lecture. Very 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 important topic, because energy storage devices are the need of the hour. They are going to be used extensively in future as well. So uh, it is for a smart grid, for a course that discusses smart grids, it's pertinent for us to discuss about the storage systems as well, right? So this is what happens with the this is all that I wanted to discuss. Let me think if there is any. Yeah, one question that you have to answer. Next week I'll ask. And yeah, that's it. Let's move on to questions. If anyone has any doubts up until now, before moving on to MCQs, any doubts? Any doubts?
Can
Yeah,
you explain the model, RC model?
yeah.
And
Okay,
that is not very clear.
yeah, I'll discuss again.
I went through the, came up to the IEEE
Mm-hmm.
publishing because sir has uh, sir has given some IEEE reference.
Mm-hmm.
So, but I had to read it. I mean, I downloaded it, and but
Mm-hmm.
cannot understand that model RC,
Okay.
double RC or infinite for having a, yeah.
Yeah, yeah. I'll talk about them. So what happens is, okay. So you have the batteries are electrochemical in nature, right? So what really happens inside of them is there is an anode cathode structure. When I say anode cathode, lithium ions from the cathode move on to an anode plate, and they are fired onto the anode plate from the cathode when they want to discharge, right? And by having this constant striking, they develop an open circuit voltage. There is a lot of chemical process that happens inside of it. I'll give you a link of a YouTube video that I saw, where they talked about the how the electron that it has, the Li plus ion, and how it affects and everything. So that is what happens. It just fires onto the anode, and that is how the electrochemical reaction takes place, and you get uh, the generation of electricity happens, right? Now, what really happens is, so it is an electric field, right? So what happens is there is an inherent electric field which is there inside the system. So when there is an inherent electric field, what really happens is this electric field this electric field needs to. So if I tell you that there is some electric field, that is some electric field component that is happening inside the structure, you'll constantly come up with like, okay, the equivalent circuit model that I can use will perhaps consist of a capacitor, because capacitor can directly mimic that reaction in some electrical sense, because that is how capacitor also operates. It has a dielectric medium, and within that medium, what it does is it just stores the energy in form of electric field. Right. So that is what exactly happens inside of the RC circuit capacitor as well. Let's come to why RC. First, there are two main components. The open circuit is modeled as a function of SOC, right? So with the function of SOC, how the function behaves, they also I mean the open circuit voltage is also affected. That is what I've shown in this graph as well, right? So that is how the 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 open circuit voltage is modeled. Now let's say there is no open circuit, so it's open circuit. There is one resistor to model the self discharge. So there can have discharge within the cell as well, right? So a cell can discharge because of the fact that it has to supply some kind of a BMS, some thermal system. Yeah, you're
You mean to
unmuted.
say internal impedance? That is
Yeah,
the internal
in
impedance of the.
internal impedance is RO. I'll come to that, but there is self-discharge as well. When you have a phone, when you have a battery, you charge it to 100%, you don't use it for a day, it will discharge, right? So why is it discharging? Because it has to power its own auxiliary units as well, right? So that is where this self-discharge, the self-discharge resistance is used to model that, and that only. The
So it is
R
the
naught.
auxiliary. So it's a.
Mhm.
Uh, is it the auxiliary, or do you mean it's the
Thermal management.
self-discharging the
Uh,
internal impedance of the battery?
internal impedance is modeled as RO. So internal impedance, you have to, when you power something, when the current flows, that is where your RO will come into play, no? Your RO
Yeah.
is,
Uh,
yes. y-
mm, no, no. Internal impedance is the cell
Okay,
impedance.
okay, okay. No, no, no. Yeah,
Mm.
I understand. But you see, let's say
Between the
that,
terminal, no, there is a
yeah,
procedure to measure. No, practically we are measuring also
there
on
is a better
site.
way. Yeah, there is a better way to say.
Mm.
There is this leakage current
Mm.
that is there inside the battery, right? To model that leakage
Mm.
current, yeah, the battery is leakage current. We use this self-discharge. So it's leakage current because the energy is lost even when it is not supplying that power. That is where self-discharge come. R not, it's used to model the losses or the losses that happens when it is supplying power. That is where R not comes. Some internal resistance it has when it starts supplying power. You understood?
Okay, terminal say where you have cable resistance and all that you want to mean to say.
Yeah,
Even
yeah,
the connector
yeah,
resistance also is there.
yeah, yeah. I mean, yes, you can say that. Yes. So, but now let's come to the RC. So what happens is, so there is this time varying, there is this time varying phenomena that happens inside the battery in which it stores power inside the electric field, that anode cathode structure. The RCs are used to model that time constant. So as you increase the RCs, you achieve that perfect sense of model that was there. By having that infinite series of RC circuits, you can model the complete phenomena that happens inside the batteries. But if you model a few, you can only capture the few characteristics varying with time. That is what
That
is
is
used.
okay. That I
Mhm,
read also, but
mhm.
the relevance of it I am not able to understand. What you're saying is written in
Yeah,
the
but
standard, but hmm.
how can I talk? So see, one way to think of it is, uh, how will you model um okay, let's say, okay, when I was discussing this, I told you, why not RL? If you want to model if you want to store energy, right? Inductors also store energy. Why not model it as RL? Why don't we model it as RL? I just explained it to you over there as well. Do you have
Yeah, yeah. Okay.
yours? Why? Because there is no magnetic field. The inductor stores energy in form of magnetic field. Here, the electrochemical procedure that is happening inside the battery, they store energy in some sort of electric field. So to model that electric field phenomena, we use RC models. You understand? Because we are storing energy in some medium. To model that medium, we are using RC. Um,
Mhm.
you have to give
Okay.
me some sort of, yeah.
Okay, let me go through that, and
Yeah,
then probably in the next, whenever you are, we can discuss.
yeah, we can discuss, but yeah, I have also read a few papers, and in that what we have seen is the as you keep on increasing the number of RC models, there is first the steep increase and then it starts getting plateaued over there, right? So you can always have it is used, so this RC can be said as to model some sort of, it is how you model the SOC, equivalent of the SOC, this RC, because you're storing energy, and that is how your RC is modeling that energy storage. So you can see that if you model it like this SOC is there with one time constant, then two time
Could you
constant SOC square. Yeah,
could you model this in any software like
yeah,
PSCAD or
yeah.
ATP?
Mayur,
Have you done
you
that? Were you able to
you
do it?
you can model it in MATLAB. I have not done it. I have not done an empirical, but I have one
Hmm.
intern who has worked on it. If you want that, I can get you that MATLAB model and send it over to you. I
Okay,
had one
Matt.
intern who worked on it. Yeah,
Okay,
I
and
did
you
not
are
work on
getting
it.
the SOC kind of SOC with that?
I have not. I don't know.
Okay.
Intern did it. I
Probably, I mean,
really
that
I
would be
worked
the
on it.
application of it, no? So for
Yeah,
simulation and modeling only is the application of this, right?
yeah, it's the model is used to simulate, right? You want to, that is what I discussed over here, right? So you want to
Hmm.
model how you would want to, the what is the practicality of a model? You want to simulate that in an electrical sense of before you use it, use your specific thing with an actual battery. So before you
Right,
use
right.
that
So
specific
this would
Mhm.
we would be able to do transient analysis also with this kind of model, or
uh see, if you use MATLAB, it's very difficult to say if you can model transient analysis,
no,
but
I'm talking about some like ETAP or PSCAD or like
see, I don't have,
ATP. Or,
yeah, I
okay,
understand. I don't have knowledge, but I feel if you
power
can
like a
model,
power system study point of view, I'm saying.
yeah, if you can model it in that software, yes, you can do transient analysis too. But I really don't have knowledge, so don't believe the what I say. But if you
Mhm.
can model it over there, I believe. But because you have transient behavior that is happening with respect to capacitor too, right? So I feel that there could be,
Mhm.
but I really don't have an answer to that. No.
Okay, okay, okay.
Yeah. Yeah. So that is what. Any other doubts if someone has? Okay. So, Mayur, one more thing that last time you asked, right? So, yeah, I could not. I was trying to answer it in a certain way, but I could have used a specific word. I'll just get back once I'll complete the lecture once. I'll just come to you. So, let's talk about the MCQs, right? So, the first, okay, so where was I? I gave you a brief recap of everything, right? So, let's move on to MCQs. So, let's solve some problems. So, the first question is, which of the following is not a type of mechanical energy storage system? Can anyone solve? So what is a mechanical energy storage system in which you store energy in some form of a mechanical energy, right? In some kind of a mechanical way. So compressed air, is it the correct answer? You see, not is there. When there is a not, you have to, okay, which is, uh,
Latent.
yeah, latent is the correct answer. Latent is a thermal energy storage system kind of a thing, right? Next, we have which of the following combinations of energy storage technologies are not feasible for hybrid energy storage system? So, in a hybrid energy storage system, you use two or more energy storage system technologies. So, to store energy, right? So, two or more, if you have, it's called a hybrid energy storage system, right? So, supercapacitor and battery, they both are different in true sense. One is high power density, the other is high energy density. Both are hybrid. Then lithium ion and sodium sulfur batteries also are hybrid. When vanadium flow and lithium ion batteries are also hybrid. So the correct answer for this would be, oh sorry, are not feasible, right? So none of these. Both are feasible. So you see, the any combination that you can develop to support one and another, or even, not even support. If you have two batteries with different architecture, you can use them to supply as a hybrid energy storage system only. Next, match the type of energy storage. So this we have discussed. So I just want someone to do it. We'll do it, but I want someone to do it first. Okay, so what is a flywheel? So flywheel, what it does is it rotates continuously. And just like I gave you an analogy, right? You go to a tailor shop. They have this sewing machine, right? They pedal it from their foot, and there is this rotating wheel which keeps on rotating even after the force has been withdrawn, right? So that's called a flywheel. And what it does is it stores that energy that you have given to it in form of kinetic energy, which can be then used to supply it to, to run some different type of. So so it is a mechanical energy storage system, right? Then you have batteries. What are batteries? Just now I gave you, it's what? Nobody's willing to answer. I mean, there are not a lot of people. That's the downside of taking the last class.
Electrochemical.
Yeah, it's electrochemical. Then you have fuel cell. It's chemical. And then you have superconducting magnetic energy storage, which is electromagnetic, right? So the correct answer is A3, B1, C2, D4. A3, B1, C2, D4. Yeah, option 3, correct. Great. Next, which of the following storage type has high energy density? Very easy. You must be seeing in your assignments, right? The questions are very easy. So this subject is very easy if you just, there's a lot of data, there's a lot of knowledge, but it's just that it's easy. I mean, it's easy for you to get grades. Which of the following storage type has high energy density? Oh, someone has wrote no. Okay, the answer is 3 only, but okay, supercapacitor, it has high power density. PD is more. It does not have high energy density. I mean, it can only, once it gets in contact with some medium, it will discharge completely very quickly. Lead acid between lithium ion battery and lead acid battery, only lithium ion battery has the highest energy density. Next, a 12-volt battery with a capacity of 500 ampere hour is at 80% SOC. Find the DOD. So what is DOD? It's 1 minus SOC, right? So 1 minus 0.8 is how much? 0.2. So in percentage, it will be 20%. Great. Next, a 12-volt battery with capacity of 500 ampere hour is at 80% SOC. Calculate the energy stored. So ET at any, so SOC is what? ET upon E rated, right? So ET is what? SOC multiplied by E rated. So what you have to do is just multiply both of them. In essence, you have to multiply 0.8 into 500. Can anyone tell me what's the correct answer for this?
400.
Yes, 400. So next, which type of problem is a distribution network planning problem? Any planning problem on the distribution network will have power flow constraints which are non-linear. So, and you can always use any kind of integer or continuous decision variables. So which kind of problem will it be? So this concept you understand, right? How linear programming problem are differentiated based on the integers and functions. So the correct answer is,
Mixed integer nonlinear programming.
yeah, these are non-linear in nature, and you can use, right? The advantage of the mathematical programming approach. Okay, this I did not cover. So When you have these optimization problem, right, you can use various different ways to solve them. One of them is a mathematical approach where you solve them using mathematics. I mean, that's what it says, right? So one quick way of solving them is by using, simplex method, or a simple method could be Lagrangian multipliers based method, right, where you decompose into dual variables and you solve it. I mean, I won't go into details about that. So there, but if let's say there is a concave function, one way is you can convexify it and you can, get results. And let's say if you have non-linear programming problem, right, and if it is non-linear, I told you solving it is very tough. Mathematically it will become very tougher for you. That is why you have to resolve to, the state solvers that are state of the art solvers available at our discretion for usage. So when the complexity of the mathematical problem increases as the complexity of the formulation problem formulation increases. If it's linear programming, solving it by hand is very easy. But if it's, let's say, nonlinear programming with very high number of constraints, very developed objective function, it becomes very difficult to solve that. So that is why a mathematical programming approach is used. But one more approach there are heuristics. You can develop heuristics, like there is particle swarm optimization problem. You get and you start your problem in very different you know and in different ways, and then you attack it so that you can converge to it one to one uh, you know one optimal point, right? But the problem with heuristics based approaches, they don't guarantee convergence. But if you solve it by hand using mathematical approach, they will always guarantee a global optimal solution. So the answer to this question is that they give global optimal solution, but they are high on computational burden, they have high convergence time, and this formulation won't be simple. It can be very hard to formulate itself. So the complexity increases as the complexity of it increases. So direct cause of permanent failure to lithium ion battery. This also I have not covered, right? I forget things, but yeah, I just say. So there are anode cathode plates, as I told you. And at the anode side, when the cathode, a lithium ion comes, what happens is there is a a solid electrolytic interface. You see, this solid electrolytic interface is very important for the battery. It is a boon as well as a bane. I'll talk about both. Why boon? It's because it wants to absorb only lithium, but once it comes from cathode to anode, it can be, some kind of, it can form some kind of, compound, let's say lithium ferrocarbonate, lithium ferric carbonate, or some kind of a lithium compound, so that it has to act as a barrier so as only to let go lithium ions from it, right? If it lets go of these compounds, it can cause detrimental effects to your battery. It will degrade faster. So if this SEI layer is damaged, it can cause permanent damage to your lithium ion battery. So the damage to SEI layer is the main cause of your permanent lithium ion battery. So it has this SEI layer which acts as a barrier and only allows Li plus ion to pass. Right? Leakage current is not, Coulombic efficiency is also not, and heavy operation. The indication of the state of charge of a battery is best given by this. Also, I told you, right? What is the correct answer? So I gave you I told you, right? How can it be used? The answer is specific gravity of electrolyte. The electrolyte inside of it, when it is charged to 100%, let's say for a lead acid battery, because that's the only place where, right? For a lead acid battery, when it charges to 100%, the sulfuric acid is at highest concentration,
This answer is not correct for nickel cadmium batteries.
Okay, why?
There is no change in specific gravity on discharge.
Okay, there is no change of
I have
specific
measured
gravity.
it, yeah, because I have measured it. Lead acid, yes,
Yes,
from
lead acid.
1200 to 1100, and this
Yeah,
there is
lead
no
acid.
change in
Yeah, lead acid. I
nickel
also know,
cadmium.
but yeah, I mean, uh, yeah, you see, the questions are very. So I'll just add a star over here, which means conditions applied. I don't know. I get these questions and I have to solve them, right? So it's only applicable as far as I know to lead acid battery.
I don't know about lithium ion.
Lithium ion, I also don't know. I tried searching for it, but there was no mention on measuring it using specific gravity of the electrolyte inside of it. So I don't have any. Yeah. So, but the question was there, and I had to solve it because I feel this could also come into your assignment. So I had to give you the correct answer too, right? So that is why I specifically told you for lead acid only. I'm talking about lead acid. That is the only reason. So we can measure that concentration with respect to the density of the electrolyte with respect to density of water to estimate the SOC. Uh, the question could have been framed very well by right of a lead acid battery, and it could have been a very very good question, but I don't know why they didn't do it. Next, which is not an active cell balancing method? Can anyone tell me? So a active cell balancing method is the method in which you transfer charge or power from the stronger cell to the weaker cell. So what is the correct answer?
Wow,
Hmm. Overcharge is not the correct answer, right? Because you are trying to dissipate the energy from the heavily charged one to the one that is lower charged. Next, why is battery management system required? I already discussed everything. Why it is required? What is the effect of BMS? Without it, what will happen? You see, the BMS has a very high crucial role to play. It helps in managing the thermals, which can help in increasing the efficiency. It helps to manage the cell balancing and everything. The optimal usage is all done by BMS, and it can reduce the risk of prematurity. So all of them are correct. So the correct answer would be all of the above. This is all given in the last lecture of the slide. So this is just taken from that slide and used. Which one of the following storage technology has not so good cycle life? So flywheel.
Super capacitor.
No, supercapacitor has excellent cycle life. Cycle life, I mean by how many cycles it can endure before reaching to a state of failure. Supercapacitor,
redox flow.
redox flow, redox flow. They gave me lead acid and redox flow. Okay, so flywheel. Let's talk about each ones, right? So a flywheel, it's kind of like a mechanical system, right? As much as you want, you can store energy from it. Any cycles, right? It just has to rotate. It does not has to no, I mean it's not discharging in some form of, let's say, which is detrimental to its effect, right? So to its health. So flywheel, talking about not so good cycle life, is not. Supercapacitor, it stores energy, it gives bursts of power, right? It is used to give bursts of power. It is not used to give power for a longer or exaggerated period of time. It is just used to supply the transients or the burst of power that is needed at certain point of time. And a supercapacitor is excellent life. You can just charge it, discharge it, charge it, discharge it, and keep it at its charged level before it can be used to discharge at a very high burst. Between redox flow and lead acid, so I checked online. I really don't have a perfect. Yeah,
I think lead acid would be
yeah,
right, probably.
yeah. The lead acid is the correct answer. The redox flow, I couldn't get the exact number, but the lead acid battery, it was around 1000 to 1500. So lead acid is the culprit here. Next, minor complexity is a significant advantage of which battery modeling methods? Okay, so I did discuss everything, right? So there are ways in which you can model a battery equivalent model as well. You can have empirical, electrochemical, or Your more physics based is electrochemical only. Or one, what is the next one? Equivalent circuit, which is mathematical. So what do you think has minor complexity? So in empirical, you just have some relations.
Empirical.
Yeah, you use those relations to model it, right? So there is no complexity at all. For an electrochemical, you have to use some equations. These are Arrhenius equation. I don't remember the exact formula. And in equivalent circuit, you have to model that correct number of RC circuits, right? So the complexity increases with the increase in RC circuit. So empirical modeling gives you the significant advantage. Next, what is the disadvantage of lithium ion battery?
Degradation effect.
Yes, it goes through a degradation, and that is the only disadvantage of the lithium ion battery. Next, suppose an objective function of an optimization problem is convex, then which of the following is true regarding the overall optimization problem? So you see, when I discussed about convex function, and if you paid attention to my class, you would answer this question very well and very quickly. So I expect an answer. Okay, so linear constraints. Uh, so if you have
Convex
linear,
concave problems are there?
if
Sorry,
there are,
sorry.
yeah, no worries. If you have linear constraints, they are always convex in nature, so they'll always be convex problems. But if you have non-linear constraints, it can so happen that they can result in a non-convex problem, but they may. It's not like they'll always, but they may. So may result in non-convex. Let's say I'll just give you a brief, right? Convex optimization problem, a very brief constraint which is there in distribution side or even the transmission side, right? In distribution side, let's say that you have a transformer at the top of your feeder, and it is limited to the maximum amount of apparent power it can store, right? So when developing the constraint, it is like s square is less than or equal to the p square plus q square coming out of it, right? So this is one constraint that, no, sorry, greater than equal to, my bad, right? So this constraint in itself is non-linear, and it is a kind of like, let's say, you know a circle. It's an equation of a circle, right? So within a circle, the points that are inside of it will satisfy that, and you have to find the optimal solution which is satisfying inside of this region. This is non-linear. This constraint is non-linear, but the problem that it will pose, it won't be concave, it will be convex. So non-linear constraint may give you a non-convex problem, but not always. So linear constraint will always result in a convex, and non-linear may result in a non-convex. So the correct answer is 2 and 4. Last, what is or are the significant advantages of the hybrid algorithms estimating battery SOC? So when you see, when you're talking about the advantages of something, right, and there is this all of the above, 80% of the time the answer would be all of the above. So if you use hybrid algorithms, you can get best of both worlds, right? If you have a, let's say, mathematical model, and you have a neural network model, right? So there is this thing called as physics aware neural network model, right? So you can have best of both worlds. So it can be more effective, it can give you high precision, and it can be reliable. A circuit model in itself can't be that effective or precise, but a neural network in that self will not be that precise. But in when you combine both of them, it could result in a very high precision, right? So the correct answer would be all of the above. So this is what I wanted to discuss this week. So the topic, the main topic, or the center point of discussion was energy storage devices, their need, how are they getting, they are being used at the distribution side, what problems they face, what is BMS and everything. We just discussed that. Yeah, so Yeah, this will be uploaded on YouTube. The PDF of the PPT will be shared with you, and you can always use the comment section of the YouTube to ask your doubts, and I can always answer them. Coming to Mayur, so you in the first you were very skeptical about the PMUs, right? So you see, I work on power markets. I really have very I my knowledge is limited to smart grids or monitoring aspects, and it's something that I should have, but I really never paid attention to. But let's come to why PMUs and SCADA and RTU we were discussing, right? So the the main advantage that you have with PMU is the resolution. That is not the word I could have that is the word I could have used when we were talking that day. I couldn't find the right word, right? That is where I failed. So when I talk about resolution, it's like how many timestamps of data it can give me, uh, within a unit of time, right? For let's say the PMU that we have developed at IIT Kanpur, it can give you 100 data, 100 timestamps, 100 data points in 1 second. So that means it's giving me data points in every 10 raised to power minus 3 seconds. Oh, sorry, 10 raised to power minus 2 seconds. Right, so the resolution is there. But with SCADA, the resolution is very less. It gives you data in 1 second to 2 second. So if you're doing steady state, analysis, or you're using that for steady state purposes, you can always use SCADA. There's no problem. It will always be better for steady state analysis. But let's say if you want to do transient analysis, you need that resolution inside of it, right? That resolution comes from the PMU. It is able to give you data very quickly within a minute. I don't know why SCADA is not able to give you, why it is not being developed. But what I feel is there is a generational difference. You are upgrading from SCADA and RTUs, and you're moving to, I shouldn't say SCADA, RTUs, and you're moving to PMUs because the resolution of the data, because now transients are coming into picture, right? Renewables are there, transients are getting affected, and you have to measure those bursts of power, bursts that can happen with your voltage and current phasors, right? And to measure that, it's better to use a high resolution device. And one more thing, they are highly accurate. The accuracy is very high. We will discuss all of this in week 4, so this is the center point of discussion for week 4 as well, but I'm just giving you because I saw your name, so I thought I should talk to you. And that is where PMUs are very effective. It's the resolution, it's the transient analysis of the system. Over to you, Mayur.
Yeah, okay.
Okay.
No, I had a discussion with one of the GE engineer.
Okay.
The lady is into power system studies since last 25 years. She is a PhD from IIT Delhi also. So
Okay.
I just asked her. She said, I think in that line we discussed, basically for to get an overview of the network,
Mm-hmm.
the 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 NLDC or SLDC get this data, and then they get the voltage and phase angle at all the buses.
Yes.
With these two values, they can calculate anything.
Yes, that is
And
right.
the second is for the electromechanical stability.
Okay.
Say a transmission is moving out of, say there could be a prescribed angle between the two transmission line nodes.
Mm-hmm.
So beyond that, if it goes out of sync.
Mm-hmm.
So if any network is going out of sync, say a western region with the southern region,
Mm-hmm.
they get that stability margins and they get an idea. I mean, the
Mm-hmm.
system is moving out of sync.
Mm. So that is what I
Not
was.
yet fully, not yet fully implemented in India. It's
Mm.
in phases.
Yeah.
It's still in under implementation.
Yeah, the main application is wide area monitoring. So that is what I was talking about, that as well. Wide area monitoring, sitting at some, or what happened? uh, okay, it was not needed. So what I was talking about is wide area monitoring, sitting at some place, some remote place. You can measure anything, any component, by just calculating the phase value of the current and the voltage, sitting at any off at any bus, right? That is what PMUs are doing. So they are very reliable too, as far as I've talked to my seniors over here. So those who develop PMUs, right? So yeah, that is what the functionality is. Yes, yes, you are absolutely right. So So anything can have any, application that can be suited to a person who is, who wants to use it. So it can be fitted to what the person needs. So it's used to calculate phasor values of voltage and current at any bus, and it can then be used for any purpose anyone wants to use it for. Yeah, so that's it for today. So I hope that the class was enjoyable. I don't know if people have started to drop. I've witnessed this last year as well, so it's not that big of a deal for me. But still, I would appreciate if there are more people joining in. And see you all next week. Next week we'll discuss about wide area monitoring systems only, and looking forward to have an interactive session. Thank you all for joining.
Thank you so much. Thank you.
Thank you. Thank you. Bye.